Okay, in this lesson we're going to be looking at finding the x-intercepts and other critical features of a quadratic equation. We're going to be looking at finding these critical features through graphing and also algebraically. Why don't you start by graphing the quadratic equation shown here, and you can put the video on pause while you do this. Okay, first step is to make an xy chart. You might be using different x values, but I'm going to use -4 to +2. When you square the -4, you get 16 minus 8 minus 3. That's going to give you +5, which is up here. Plot -3, that's 9 minus 6 minus 3, which is 0. Next point is going to give you -2, -3. Next point is -1, -4. And then when you plug in 0, you get -3. Now I want to talk about this point for a minute. 0, -3 is your y-intercept. And if you notice, when you plug 0 into the function, the quadratic term and the linear term both drop out, and you're left with -3. This constant value, no matter what it is, will always be your y-intercept, because when you plug in 0 for x, all the other terms drop out, and you're left with the constant term. So c, the constant term, will always be your y-intercept. Moving on, when you plug in 1, you get 0, which is here. Plug in 2, you get 5. So here's our parabola. Let's talk about the x-intercepts. Looks like the x-intercepts lie at -3 and +1. These x-intercepts are a really critical part of this unit. We're going to be looking at 5 different techniques for finding these x-intercepts. And because there's so many ways to find the x-intercepts, they also have a lot of names. They're called x-intercepts, of course, but they're also called the solutions of the quadratic equation. They're also called zeros, and we'll talk about why they're called zeros in a second. And they're also called roots, which we'll get to in a few lessons. The zeros of a function are the x values that make the function equal to 0. Let's graph y equals x squared minus x minus 6. When you want to find the y-intercept of any function, what you do is you set x equal to 0. Now when you do that in this quadratic, the quadratic term and the linear term both drop out, and you're left with the constant term, y equals -6. That's going to be your y-intercept. That c value will always be the y-intercept. So I'll plot that on the graph. Now let's look at the x-intercepts. You remember back when we did linear equations, when you want to find the x-intercept, you set y equal to 0. So when I set y equal to 0, I get this. Now, this quadratic equation has solutions, but I have no way of knowing what they are yet. There are 5 ways to solve this quadratic. I don't know any of them yet. So I have no means of solving this type of equation yet. You might think, well, can't you just get the x's on one side? Well, you could, but there's no way to combine these x's. You can't combine an x squared with a -x, so there's no way to solve it like you would a linear equation where you get x on one side and your numbers on the other. So we're going to have to look at different means for solving these types of equations, these quadratic equations, and we'll get to that. Right now what we're going to do is graph this and see where our x-intercepts are. I'm plugging in -3 to +3 for x, and I'm going to graph this pretty quickly here. And we see that the x-intercepts are here at -2 and +3. Those x-intercepts are also the zeros to the equation. Why are they called zeros? Because if you plug in -2 into the equation, you get 0 for y. And when you plug in +3 into the equation, you get 0 for y again. So that's why they're called zeros. They're called solutions because these x values also solve this equation up here. If when you plug in -2 and you square it, you get 4 minus -2, which is +2. So you end up getting 4 plus 2, which is 6, minus 6, you get 0. And the same thing happens when you plug in 3. You get 9 minus 3 minus 6, which is 0. So they are solutions to that equation. And they are also the x-intercepts of this parabola, so that's easy to see. And we'll talk again later about why they're called roots. So now let's find the zeros of these quadratics. What we're looking for is the x-intercepts. The x-intercepts are the zeros. That's x equals -1 and x equals +2. So I'm going to check that by plugging -1 into the equation. I should get 0. And indeed in this case I do get 0. Now when I plug in 2, I should also get 0. And I do. So -1, 2 are the solutions to this equation. They are also called the zeros, the x-intercepts, a lot of different names for them. Problem number 2, looks like the x-intercepts are -3 and +1. So when we plug in negative 3, will we get 0? Yes, we do. We get 0. When we plug in positive 1 into the equation, do we get 0 for y? Yes, we do. That's why these are called the zeros. They're also called the x-intercepts. They're also called solutions and roots. Let's look at these two functions. In number 3, there are no x-intercepts. There's a y-intercept, positive 2, but there are no x-intercepts. This parabola actually lies above the x-axis and it never crosses it. So this parabola has no zeros, no x-intercepts. In problem number 4, it's the rare case where the parabola, the vertex is right on the x-axis. The parabola touches in one point only and then turns around and goes back down. So that one value, that's your x-intercept. And when you plug it in, you get 0. It's the only value that'll produce 0 for y. So 1 is your only solution. So it's possible to have 2 x-intercepts, no x-intercepts, or 1 x-intercept. Alright, let's move on to the critical features of parabolic curves. In every quadratic equation, there is a quadratic term, there is a linear term, and there is a constant term. The value of a will determine a few things. If your a value is positive, then that means your parabola is going to open up. If your a value is negative, then that means your parabola will open down like this. If your a value is greater than 1 or less than negative 1, it's going to cause it to be skinnier than normal. Now, if your a value lies in between negative 1 and positive 1, like it's a fraction, positive or negative, it'll cause that parabola to be wider than usual. This might be a parabola with an a value of, say, 1/4. A equals 1/4. Your c value determines your y-intercept. If your c value is positive, that's going to shift the parabola upward. A negative c value will mean the parabola is going to shift down. Now, the b value does some really strange things to the quadratic, and I'll let you discover that on your own. But one thing I will say about it is your b value will shift your axis of symmetry right or left. If there is no linear term, then your axis of symmetry will be x equals 0. It'll be right on the y-axis. But if you do have a linear term, it could move right or left depending on the linear term. Okay, so now let's find the critical features of this quadratic by graphing. Okay, so you made an xy chart. You probably use the values negative 3 to positive 3 like I usually do. Now when you plug in negative 3, you're going to get some really large values for negative 3 and negative 2. These are too large to graph, so I wouldn't graph those. When you plug in negative 1, though, you do get 9, and I can fit that on the graph. 0, of course, will be 2. That is the y-intercept. Remember, that is the c value here, 2. So that'll be right here. And we'll continue down our xy chart. We get 1, negative 3, 2, negative 6, 3, negative 7, and I still can't quite tell if I've hit the vertex yet, so I'm going to extend my xy chart a little bit, and this happens sometimes where you have to extend your xy chart. I'll plug in 4 and 5. Let's see, 16 minus 24 plus 2 would be negative 6. Okay, so I can see where the vertex is now, and when I plug in 5, I get negative 3, and I can use symmetry to get the next few points, and there's my parabola. So, what's the vertex? Well, it's at 3, negative 7. Notice my axis of symmetry always goes through the vertex, and that's always going to be the case. Whenever you know the vertex, you will also know the axis of symmetry, because the x-coordinate of the vertex is the same as the axis of symmetry. And if you know the axis of symmetry, you will also know the x-coordinate of the vertex, because those will always correspond. Alright, the other thing we want to look at is the minimum value, which we know is the y-coordinate of the vertex. Y equals negative 7. That's the smallest value that y can be. So looking at this again, the axis of symmetry is the same as the x-coordinate of the vertex, and the minimum value is the same as the y-coordinate of the vertex. Now if the parabola were to open down, if this x squared term had been a negative, then we would have a maximum value, and that would be the y-coordinate of the vertex. Let's do this same equation again, but this time we're going to do it algebraically. Now we remember what it looked like before. The first thing we have to do is know the formula for the axis of symmetry. And that formula is x equals negative b over 2a. You're just going to have to memorize that formula. Where do a and b come from? They come from the general form of the quadratic. All you need to do is look at your equation. The coefficient of the x squared term is going to be your a value. So our coefficient of this x squared term is 1, so that means a is equal to 1. The b term, the coefficient is negative 6, so b is negative 6, and then c is 2. We don't need the c value for this equation, but it doesn't hurt to write it down. So when I substitute negative 6 in here for b and 1 in here for a, I get negative 6 over 2 times 1, which is positive 6 over 2, or x equals 3. That is our axis of symmetry. And if you compare that to the graph we just made, you'll see that it matches. Now the vertex. The vertex lies on the axis of symmetry. Since we know the axis of symmetry is x equals 3, that means the x-coordinate of the vertex is also 3. So how can I find the y-coordinate now? Well, once you know the x-coordinate of the vertex, it's easy to find the y. Just plug it into the equation. You have an equation that relates x and y. So if you plug 3 into the equation, you'll get 9 minus 18 plus 2, which comes out to be negative 7. So our vertex is 3, negative 7. Now remember, the vertex is a coordinate point, and it should have parentheses around it, 3, negative 7. The axis of symmetry is a line. It should be x equals 3, not just 3. Okay, next thing we're going to look at is, does this parabola open up or down? Well, it has a positive a value. A is equal to positive 1, so we know that this parabola opens up. Now, if you can visualize it opening up, does it have a max or min value? Well, if it opens up, that means it's going to have a min value. What is that minimum value? That minimum value is going to be the y-coordinate of the vertex. So y equals negative 7 is your minimum value. What is the y-intercept? Well, that's the c value. The y-intercept is c equals 2, or you could write that as 0, 2. So those are the critical features of this quadratic, and we found them all algebraically without graphing. If we compare these to the graph we made earlier, we see that they match. The axis of symmetry was x equals 3, the vertex was 3, negative 7, and the minimum value was y equals negative 7. Let's do it again for this equation, which we've never graphed before. Okay, axis of symmetry. Formula is x equals negative b over 2a. These are, my a value is negative 2, b is 8, c is 0, because there is no c value. There's no constant in this equation. When I plug those values into my equation, I get x equals 2. That means the x-coordinate of the vertex is 2. When I plug that into my equation to find the y value, I end up getting negative 8 plus 16, which is positive 8. So my vertex is 2, 8. And remember to put parentheses around that ordered pair. All right, does this parabola open up or down? Well, the a value is negative 2, so this parabola opens down. When a is negative, it opens down. Now think about this. If it opens down, does it have a max or min value? Well, if it opens down, it has a max. What is the max? It's the y-coordinate of the vertex. Y equals 8. That is your max value. And we said before that there is no constant term, or the constant term is 0, so that means your y-intercept is 0, 0. All right, let's take a minute to try this one. You might want to pause the video here. Okay, axis of symmetry. You should have got x equals negative 2. Vertex comes out to be negative 2, negative 8. Since a is a positive 3, this opens up. Because it opens up, it has a minimum value, and that minimum value is y equals negative 8, the y-coordinate of the vertex. The constant is 4, so that means your y-intercept is 0, 4. All right, now let's take a look at how these critical features play a role in the real world, in projectile problems. Let's say I have somebody throwing a baseball up into the air. We're going to take a look at the height of that baseball over time in seconds. That baseball is going to follow a parabolic curve. It's going to go up and then it's going to come down. It's going to have an initial height. Now, if it were a soccer ball and you were kicking the ball off the ground, that initial height might be 0. But with a baseball, you will have some initial height. You will also have an upward velocity depending on how high you throw it. And that is going to affect how long it stays in the air. And you also have acceleration due to gravity. So these are the 3 factors that will affect how that parabolic curve looks. And the height is going to be given by this formula. It's going to be negative gt squared, because gravity has a negative effect. This is the gravity component, and it has a negative effect on the height. The upward velocity has a positive effect on the height, because the larger that upward velocity is, the longer it's going to stay in the air, and the higher it's going to go. And you have an initial height, which will also affect the height that it eventually reaches. So this is our general formula for any projectile. So now let's take a look at a real-world problem and see how this would be used. A rock is thrown from a cliff with initial height of 25 feet and an upward velocity of 100 feet per second. Acceleration due to gravity is 16 feet per second squared. Write an equation that describes its height h over time t. Well, we know the formula, so we'll start with that. We know the initial height is 25 feet, the upward velocity is 100, and acceleration due to gravity is 16 feet per second squared. So we'll just plug those values into our equation, and we will get a very simple equation that describes the height over time for this rock. The rock goes up and it comes down. Now, there are several different questions I could ask once you know this equation. I might ask, what's the maximum height reached by the rock? If I ask that question, then what you are looking for is the y-coordinate of the vertex, because the vertex represents the highest point reached by the rock. The y-coordinate represents its height, and the x-coordinate represents the time that has gone by before it reaches that height. I could easily ask two questions here once you know the vertex. I could say, when does the rock reach its maximum height? And I could also ask, what would be the maximum height? If I ask, when does it reach its maximum height, then you're looking for the x-coordinate of the vertex. If I ask what that height is, then you're looking for the y-coordinate of the vertex. I could also ask when it hits the ground. What critical feature of the quadratic would I be looking for then? If I said, when does it hit the ground? I'd be looking for the x-intercept. That is correct. So now let's answer one of those questions. How would I find the max height reached by the rock? Well, I have the equation. What I need to know is the vertex, specifically the y-coordinate of the vertex. I can do this algebraically by first finding the axis of symmetry. I'll use my formula, x equals negative b over 2a. Once I get this, I'll know the x-coordinate of the vertex, and then I'll use that to find the y-coordinate of the vertex. So I plug in my values, and I get negative 100 over 2 times negative 16, which is going to be negative 100 divided by negative 32, which is 3.125. So after 3.125 seconds, it reaches its max height. Now let's plug that into the equation to find the y value, which is really what I'm interested in, the max height reached by the rock. So I plug that in, and using a calculator, I come up with 181.25 feet. That is the maximum height reached by the rock, the y-coordinate of the vertex. Now let's look at another similar problem. A baseball is hit with an initial height of 1 meter, initial upward velocity of 32 meters per second, and acceleration due to gravity of 4.9 meters per second squared. So we're going to write an equation to describe its height over time. We know that initial height is 1 meter. We know the upward velocity. We know the gravity. We'll plug that into our equation. There's our equation. Now let's use that equation to find the maximum height of the ball. The axis of symmetry is where we'll start. We'll plug in our values. We end up getting x is equal to approximately 3.27 seconds. That's when it reaches its maximum height. The x-coordinate of the vertex is 3.27. If we plug that into the equation, we'll find the max height. And in this case, it comes out to be about 53.24 meters. So here we see some practical application of these critical features of quadratics, and in the future we're going to be looking at many different types of problems that can be solved using quadratics like this.